you. So I would like to thank the organizers for giving me the opportunity to present my work. I'm Stéphane Aicardi. I work at the Paris Observatoire in the IT department. And I'm also a member of a scientific project called Minerva, which is working on machine learning on radio astronomy. So we'll talk about trying to recognize Jovian Decametric emissions with deep learning techniques. So first, what are those emissions? So since the 50s, radio astronomers have observed radio emissions coming from Jupiter, mainly in the decametric range. Those emissions now are known to be produced by the cyclotron maser instability, and it's due to either the solar wind or to Jupiter Io electrodynamic interactions. And we can see the counterpart in the visible range in this picture, where we see the auroras on Jupiter viewed by the Hubble Space Telescope. These emissions come in many timescales. In the very short range, we have the S-bursts. Then in the moderate timescales, we see arcs in the time frequency plane. Then they were used to characterize the rotation of Jupiter's magnetosphere. And on the larger scales, we can see the response to solar wind and the interplanetary shocks. Here is a diagram that shows the different types of emission that can be observed in the decametric range. The emissions are polarized. So when they are right-hand polarized, they come from the northern hemisphere. When they are left polarized, they come from the southern hemisphere. We can see those arcs that are curved this way when they come from the dusk side, taking the rotation of Jupiter into account. When they are on the downside, they have this shape. And so we classify them as A, B, C, and D. And some are due to IO, and some are due to other causes. So that makes 8 types of emissions. Here we represent the probability of occurrence. Here we have the order of the longitude of Jupiter magnetic the Jupiter axis, and here we have the phase of Io viewed from the observer, and we can see the 4 types of emission on this diagram. That's how those emissions have been linked to Io. Then here is the non-static decameter array, which I have used for the observations. So it was built in the 70s, and now it has numerical data since the 90s. It had many receivers. I used mainly the routine one, which produces small data. But I want to point out that the Juno N receiver produce lots of data because of its resolution in time and in frequency. And if we wanted to keep all the data, you can calculate 3 terabytes per day for many years. It would be intractable. So we need to select the observations of interest, and I think my work is a step in this direction. So this is what we can observe. Here we have a IOC and IOD occurring simultaneously. IOA simultaneously. Here we have IOD and IOB occurring simultaneously. Here we have non-IO emissions, non-IOA, non-IOB, non-IOC, and non-IOD. Those emissions have been successfully simulated by Corentin Louis, which has built a software that reproduces most of the observations, and we host a run-on-demand server to use this simulator with whatever parameters that you like, and it's publicly available. And now onto my part. So at first, the data looked like this. So we see a lot of things, but where are the real scientific data? In fact, it's hidden here, but we have lots of RFIs. We have calibration data every hour. And we also have saturations of the receiver that are a bit annoying to clean the data. But Manilo Marquez has built a catalog of 26 years of emissions, so that's a lot. Each emission has been characterized by its type, its polarization, time range, frequency range, and it drew polygons over the emissions. So here is a representation of each type. We have here IOA and its counterpart in the left-hand polarization. We have here non-IOD and so on. Using this catalog, we can try to do some trained machine learning networks. We have many types of classification problem. First, we can just classify. So in machine learning, it's always cats and dogs. So here they are. We can then try to localize. So finding the bounding box around the object and the type of the object and its probability. Then we can try to do a semantic segmentation. So it's the object is to colorize each pixel of the image with a color that corresponds to its type. So we have here the road, we have people, street signs, trees, and the sky. And we can also do instance segmentation. So here we have 3 cats, and each cat is labeled differently. So in my part, I did mainly basic classification and semantic segmentation. First, with classification, so I used samples that contain only one type of emission, no simultaneous emission, and use it to train a convolutional network that gives me 80% of correct classifications. And if I use the data of the ephemerides, I can climb to 88%. So it's promising, but I thought I could do something better, and I tried to do a semantic segmentation. So I'll detail a little. First, I cut samples of 5,000 seconds into the observations. Why those 500 seconds? It's because emissions usually last less than 1 hour. So one emission should fit in the sample. Try to clean the RFIs and clean calibration, background, and filters, and normalize the data to help the network. Then reduce the samples to a size 400 by 400 by 3. The 400 for the frequency is the full range of the receiver, and it's better to have square data to use a convolutional network. For the output, I segment into 9 types, so nothing, IO, A, B, C, and D, and non-IO, A, B, C, and D. And I reduce to 100 by 100 to have a kind of small network. So lots of data in the training set and in the validation set. For the network, I use a UNet architecture. I used efficient net B0 as an encoder, which is one of the best network for ImageNet, and a simple convolutional decoder. And I use also a fully connected network to calculate the probability of detection of an emission. So in my samples, some have an emission in it and some don't. In the end, here is what I obtained on the same image as before. Oh, sorry. I obtained about 97% of success for the detection of an emission, and the IOU is about 93%. So I think the IOU is really interesting, but most of the observations are background, so that's makes a big IOU on this part. Next, I built some visualization tools to check the results of these neural networks. So here are the links, but in fact I'm refactoring it, so we should wait to see the next version. I also built a probability check for an emission that allows us to see if the prediction on newer data is correct. And here is an example for data that aren't in the catalog. So it's the 3rd of March. We have IOB that's detected by my network, and I can see that at this time we are in the middle of the IOB region, and Express tells me also that there should be something in that looks like an IOB. So on this case, it seems great. Then try to apply this to another kind of emissions, because it seems that some of the non-IO emissions may be due to Ganymede and Europa. So that's a work from Philip Zarka. And then I'm currently trying to provide more visualization options in the portal to see the difference, to see the probability of the prediction, and have to do more validations, because I mainly did some samples, but not something thorough. Then build the tab service with the original catalog and the predictions with, sorry. And one of the objectives is to do the detection in real time. By real time, I mean in about an hour, and to signal it either with VO events, or to just to tell that we need to archive the high resolution data. And thank you.